Welcome back, my dear students, on a new lecture on functional analysis. So, in the previous lecture, we have proved that on a closed subspace of a Hilbert space, Y and Y double annihilator or Y and Y double perp are actually same. Now, on that regard, if you consider Z as Y perp, so then Z perpendicular is actually equal to Y perpendicular or Y double annihilator, which is when a space is closed, which should be equal to Y. Now, every Hilbert space can be written as the direct sum of two operators, two spaces. So, Z can be written as direct sum of Z and Z perpendicular. Now, based on this, we can define a map PZ which maps every element in H onto some element in Z. So X to Z, where Z is actually an element in Z, where Z is the Y perpendicular. This is another map which is similar to what projection is defined, and it has all the similar properties of projection as well. So it's an exercise for you to prove that PZ has all the same properties as the projection map. Okay. Now we are moving on towards a new set of property using the annihilator and its characterization with regards to the denseness of a space. So the result is for any subset M which is not an empty set of a Hilbert space H, the span M is dense in H, that is M closure is equal to H span M closure. Span M closure is dense in H, its closure is equal to H if and only if M perpendicular is equal to set 0. This is called the characterization of sets in a Hilbert space whose span is dense. Characterization of sets in Hilbert space whose span is dense. So what we have to prove is M എന്ന് പറയുന്ന ഒരു നോൺ എംപ്റ്റി സെറ്റ് അതിൻ്റെ സ്പാൻ എച്ചിൻ്റെ അകത്ത് ഡെൻസ് ആകണമെന്നുണ്ടെങ്കിൽ എമ്മിൻ്റെ പെർപെൻഡിക്കുലർ എമ്മിൻ്റെ അനിഹിലേറ്റർ കണ്ടെയ്ൻസ് ഓൺലി ദ സീറോ എലമെൻറ്റ്. ദാറ്റ്സ് ദ പ്രൂഫ്. സോ ദിസ് മീൻസ് ദാറ്റ് നമുക്കൊരു ഹിൽബേർട്ട് സ്പേസിനെ സ്പാൻ ചെയ്യുന്ന ഒരു സബ്സ്പേസ് കണ്ടുപിടിക്കാൻ പറ്റും യൂസിങ് ഓൺലി ഡിഫൈനിങ് സം സബ്സെറ്റ്സ്. If you are able to find a subset M whose annihilator contains only the zero element, then that set actually span of that set is actually dense in H. Okay. So ഒരു പ്രോപ്പർ സബ്സെറ്റിൽ നിന്ന് സ്പേസ് ആസ് എ ഹോളിൻ്റെ ഒരു ജനറൽ പ്രോപ്പർട്ടി നമുക്ക് കണ്ടുപിടിക്കാൻ സാധിക്കും. Because span M is dense in H means every element of H can be generated using the elements of span M. So if you are given with any particular set M which is whose annihilator is set 0, using that set you can actually constitute the whole space H. That's the idea. So let us prove this. Here we have to prove two things. First thing is assume that the span M is dense in H. Then we have to prove that M perpendicular is equal to set 0. And the second thing which we have to prove is if M perpendicular is equal to set 0, we have to prove that span M is dense in H. So let's move on to the proof. Proof. Let V is equal to span M. Assume that span M is dense in H. that is V closure is equal to H. We have to prove that M perpendicular is equal to 0. So for that, consider an element, X element of M perpendicular. And we have to prove that X is equal to 0. Now X element of M perpendicular is a subspace of H, which means X element of H. And since H is equal to V closure or spanum closure, we can find corresponding to this X, we can find a sequence in V which actually converges to X. That is, there exists a sequence Xn such that Xn converges to X. Now, since X element of M closure, so M perpendicular, and M perpendicular is actually perpendicular to V, which is spanum. Because if you consider an element X and which is an element in M perpendicular, so XV or XXI, inner product XXI should be equal to 0 for all Xi belongs to M. Now consider spanum, which is equal to V, and arbitrary element Y, which is element of V. Now Y is actually element of spanum, so Y can be written as a linear combination of this. So Y should be equal to summation I is equal to, I say 1 to K alpha I Xi, let's say. So inner product X Y should be equal to, or Yx should be equal to some alpha I bar, summation I is equal to 1 to K alpha I bar inner product Xi, and inner product Xi is always 0, and alpha I bar times summation should be equal to 0, which means Y is an element, Y is orthogonal to M, Y is orthogonal to X. So which means that Y, since Y is arbitrary, every element of Y is orthogonal to every element of X, which is in M perpendicular. So that is M perpendicular is orthogonal to V, which is equal to spanum. Now, since this is true, Xn is a sequence in V, since Xn is a sequence in V, and M perpendicular is perpendicular to V, we have inner product Xn or Xnx should be equal to 0. For convenience, I take inner product Xnx is equal to 0 for all n. Now, we can write this, since this is 0, limit n tends to infinity, inner product Xnx should always be 0. Or you can write using the continuity of inner product Xnx converges to inner product Xx. I can write that as well. So this can be written as, this is limit n tends to infinity Xn x is equal to 0, which implies limit n tends to infinity Xn is x. So inner product Xx should be equal to 0, which implies norm x the whole square is equal to 0. So which implies norm x is equal to 0, which implies x is equal to 0. So we have started with an x which is an element of M perpendicular, and we have proved that x is equal to 0. Since x is arbitrary, every x element of M perpendicular should be equal to 0. So which means that M perpendicular only contains the 0 element if span M is dense in H. Here the argument that spanum is dense is essential because without which we cannot find a sequence xn such that xn converges to x, and without which we cannot say that inner product xn x is equal to 0, and which further implies that x is equal to 0. So that's an essential argument. Okay, so the first part is been proved. Whenever spanum is dense in x h, M perpendicular is equal to only set 0. So conversely, assume that M perpendicular is equal to set 0. We have to prove that span M is dense in H. We have to prove that V closure is equal to H. V is actually span M. We have a result which I think I'll give you an exercise for you to prove. If A is a subset of B, then B perpendicular is a subset of A perpendicular, or annihilator of B is a subset of annihilator of A. I think you have already studied this. Using this result, we can say that M is a subset of span M. Okay, this is clear. Then using this, which is V, using this result, we can say that V perpendicular is a subset of M perpendicular. Okay, so using that argument, we can say that V perpendicular is a subset of M perpendicular. M perpendicular is equal to set 0. So V perpendicular is actually a subset of set 0, only singleton element. Thus, for every x element of V perpendicular implies x element of M perpendicular, which implies x is equal to 0. So which implies that V perpendicular only contains 0 elements. So V perpendicular actually equal to set 0 because V perpendicular is a non-empty subspace. Okay, so M is a non-empty subspace. Its span is non-empty. So its perpendicular should contain at least 0 elements because 0 element is contained in every space. Okay, so 0 set to 0 is always a subset of V perpendicular, and V perpendicular is a subset of set 0 implies V perpendicular is equal to 0, set 0. Now V closure is a closed subspace of H. Then H can be written as, by theorem 3.3.4, which can be written as V closure direct sum V closure perpendicular. We can write as this direct sum. Now V perpendicular is equal to set 0. Thus, and V always subset of V closure by using the previous result, which implies V closure perpendicular is a subset of V perpendicular. So V perpendicular is equal to set 0, which implies V closure perpendicular should be equal to set 0 because the annihilator at least contained the set 0 or the 0 element. Okay, so if you substitute that onto this, H becomes V perpendicular or V closure direct sum set 0, which is actually equal to V closure, because this means that every element x can be written as some y plus 0. Okay, if you take y as 0, is which is true for every vector space, which is actually more correctly it should be equal to x plus 0. So x should be equal to V closure. That's it. So thus we have proved that H is equal to V closure, V is spanum, H is equal to spanum closure. That is, this space is dense in H. So if M perpendicular or the annihilator of M is equal to set 0, then spanum is dense in H as well. So using this result, I think we can easily find a space or subset which is actually dense in H. The only thing which need to establish is that for a given non-empty set, establish that its perpendicular space is actually set 0. If that happens, then the set span is actually dense in H. That's the idea. So the thing is, we can get an idea about the whole Hilbert space using a proper subset whose perpendicular is equal to, or whose annihilator is equal to, the zero element only. That's it. Thank you.